Thank you for this wonderful opportunity and conference and for listening. So I'm Ilya Besedin. I'm a postdoc in the group of Andreas Wallraff at ETH Zurich, and I do experiments with superconducting qubits, specifically error correction, and this is our recent result that appeared in Nature Physics about lattice surgery. Okay, I don't think I need to motivate quantum error correction a lot, but I'll still try to do it. So quantum computing promises that it will solve some interesting problems, will help us simulate quantum systems, and probably some pure math problems like factoring. Maybe something else, you tell me. Obviously, we're interested in the results of these computations, and they should be correct, at least sometimes, to be useful. And if you look at current quantum processors, quantum devices, you'll see that the error rates per elementary operation, like a single qubit gate, a 2-qubit gate, they're around 10 to the minus 5. I'm being gracious, it's usually much worse. But for these practical applications at the scale that we care about, we need errors about 10 to the minus 12. So there's a large gap. And the idea is to use redundancy and quantum error correction to bridge that gap. So I work with superconducting qubits. Superconducting qubits are electrical qubits, meaning that our quantum degrees of freedom are voltages. And then if this circuit that I'm showing here, that's a bit like an LC circuit. So you have the C, the capacitor, and you have this thing. This thing is a Josephson junction. It's a bit like an inductance, but a nonlinear inductance. And then you can write down the Hamiltonian of this circuit. And to write down the Hamiltonian, you need to know what the coordinate is. So your degree of freedom, what is the quantity that the wave function depends on. So it turns out that the thing that the wave function depends on is the flux, so the antiderivative of voltage, and the canonically conjugate momentum to that coordinate is the charge, so the antiderivative of current. Okay, so if you have this Hamiltonian, you can just diagonalize it, see what the energy levels are. So it's a cosine potential. At the bottom of this cosine-shaped well, you have some harmonic oscillator-like looking wave functions and almost equidistant spacing, but not quite. Physically, since this is an experimental talk, I need to show you some samples. So physically, there's a silicon chip, so block of silicon, and it's dark gray here. And then you have this light grayer thing, which is niobium on top of it, so a superconductor. And these colorful pieces are also niobium, but I colored them in paint so that you see what the qubit is. So this yellow thing corresponds to this piece of superconductor here. And then there's other things that are there to do various things. For example, there's a flux control line which changes the effective inductance of this Josephson junction according to this law. So you change this phi x, and then you get a different EJ. You have a resonator for readout using circuit quantum electron dynamics, which I won't talk about, but it does readout, so you can measure the state of your qubit. And then you have these blue wires connecting to other qubits like this for qubit-qubit coupling through mutual capacitance. Okay, I'll use the fact that Josias gave a lecture. 3 parts. So I'll just immediately start with the fact, since I'm doing surface code, you need to measure stabilizers, and these stabilizers are products of 4 Pauli operators on neighboring qubits. How do we do that? So we have these 4 data qubits on which whose Pauli operators we want to multiply and measure. And we do that with an auxiliary qubit shown in black here. So the idea is you initialize this auxiliary qubit in some ground state, and then you do C0 operations where the control is the data qubit and the target is this auxiliary qubit, and then you just do these C0s for all data qubits, and then if you flip the auxiliary qubit conditioned on the data qubit states even amount of times, and it ends up in the in the 0 state, so in the initial state. If you flip an odd amount of times, it ends up in the E state. So it's a difference. When you measure, you see the difference, but you cannot tell which data qubit contributed to this. So now what we actually do is kind of similar, but a bit different, because our qubits don't natively have the CNOT gate, they have the CZ gate. So we have to do a basis rotation on the auxiliary qubit first. So we do a pi-half rotation, then the CZ gates, then another pi-half rotation and a measurement. So it's kind of the same. And we additionally do these pi pulses on the data qubits in the middle to get rid of some low frequency noise that is easy to get rid of this way. So it's a cheap way to improve the performance. Yes. Okay, then the first thing you can do a memory experiment. So you prepare the logical 0 state or the logical plus state, and the logical 0 state is prepared by just not doing anything to the qubits in the beginning. They begin in the 0 state, and you just measure these Z-type stabilizers for the whole surface code, and then the X-type stabilizers, and then the Z-type again. And after repeating this several times, you can see that the logical degrees of freedom, they kind of have the same value as before, except it decays with time. So you can preserve the state, and like you can include the results of the mid-circuit measurements of the stabilizers and do some error correction. You can not do that. You can see that if you actually correct errors, it's better than not correcting them. Yeah, that's a memory experiment. The nice thing is that Google have shown recently that as they increase the size of the code, the lifetime gets better. So we have reached, we're in the above threshold limit. I mean, Google are at the above threshold limit. We're still close to the threshold. And yeah, so error correction works, at least for them. But I don't want to talk about memory so much. I want to talk about gates, because with memory, the only thing you see is you prepare a state and you just do error correction and see how it gets worse over time, not a computation. How do you do gates? So first of all, there's transversal gates, like for example in this paper from Harvard, from Misha Lukin's lab. And they are doing Rydberg atoms. And the nice thing about Rydberg atoms, you can move them around. So you have these optical tweezers, and you can just put two qubits next to each other and do a CNOT gate between them. And you can do that for each pair of data qubits of two different surface codes. And then you will get a logical CNOT gate between the two surface codes. So pairwise CNOTs on the data qubits result in logical CNOT between the logical qubits. Now, my problem as a superconducting qubit guy, I cannot move my qubits around. They pretty much stick to the silicon slab. They're not going anywhere, so I have to do lattice surgery. So lattice surgery, you can think the following way. Imagine you have an infinite grid of qubits. So the red ones are the data qubits, the green and blue ones are Z-type and X-type auxiliary qubits for measuring the respective stabilizer type, and patches on this grid are logical qubits. So I have two logical qubits here, and what I mean by logical qubit is that I measure these stabilizers. So the one, the other, and so on, and the other qubits I don't do anything with them. So they're inactive ones, they're just lying there. So one operation that I can do, I can merge these two by initializing the data qubits in between and extending the Z-type stabilizers such that they include those new initialized qubits, and then I measure the X-type stabilizers in between, okay? And this constitutes a merged operation. Now I have one logical degree of freedom instead of two. I can also split, so I can stop measuring those X-type stabilizers and read out the middle column of data qubits. And when I do this sequence, this results in a measurement of a two-qubit observable, and in this case, the XX observable. I'll get back to this later. You can also construct CNOT operations from this, as was demonstrated in the lecture, for which you need to extend one qubit, then split it, then merge these two, and yeah, contract the one, and that's a CNOT. And I won't go into detail why that is. Was covered in the lecture. Good. So indulge this experimental slide, please. So we have a chip with 17 qubits. I'm very happy that we do. Now that all the experimental work has been condensed to these two pictures, so someone designed this and fabricated it. Spent a lot of time. Someone tuned up gates, meaning that you can execute them with some fidelities. So the single qubit gates with an error of around 10 to the minus 3, 2 qubit gates with an error of about 2 times 10 to the minus 2. And readout, okay, we have auxiliary levels on the qubits. So I'm saying 3-state readout. Don't worry about that. I won't talk about it. The readout error is around 1%. And as an integral metric, if you have those stabilizers, how frequently do you get an error when measuring weight 4 stabilizer, meaning a product of 4 data qubits, around 18% of the time. And if it's just on the boundary, so there's just 2 data qubits, you get an error about every 11% of the time. Okay, so I have 17 qubits. It's a 3 by 3 patch on the data qubit lattice. This is also a distance 3 rotated surface code. And yes, so the operators of the logical qubit can be defined as products of data qubit Pauli operators. So for the X logical operator, it would be the product of the X operators of these 3 qubits. So I call them D2, D5, D8. For the Z logical operator, it's these 3. You can define them in various ways, but I like this definition for reasons that will become clearer a bit later. So if I do the lattice split operation by reading out this middle column of data qubits in the Z basis and stopping reading out these X-type stabilizers, then I end up with 2 repetition codes, 2 bit flip repetition codes. So I still have the Z-type stabilizers, but I don't have any X-type stabilizers. Now for the surface code qubit, any single bit flip and phase flip would be detectable. So it's fault tolerant against single qubit and single gate errors in this circuit. Whereas the bit flip codes are only fault tolerant against bit flip errors, but not phase flip errors. And the definitions of the logical operators are the following, so this naturally extends. Okay, so when I do this split operation, I get from 1 degree of freedom, well, logical degree of freedom, I get 2 logical degrees of freedom. Where does the new degree of freedom come from? It's actually the product of the X operators, so the thing that would be measured if you merge and then split. Now I just split, so I get this new degree of freedom. This XL1, XL2 would be set to the outcome of the stabilizer operators before the split. Okay, so I have these 4 operators, the stabilizer operators. Now I don't have them anymore, but I have the logical degree of freedom. And what I want is not a state that depends on the measurement outcome, but I want a state that is reproducible. So what I do is I do this split, but then I do a Pauli frame update. So I redefine my logical operators such as that they include these stabilizer measurement outcomes. Okay, and I also redefine my Z operators in a way. Okay, probably it's better to look at this circuit here. So I have this measurement, this split operation. It's like an XL1, XL2 measurement. And then depending on the outcome of this measurement, I do a Pauli gate on the qubits. And I do them in post-processing. So I actually execute the whole algorithm. And when I read out everything, then I do it like already days after the experiment. And I can do that because this is a Clifford circuit, and these are Pauli operators, and Pauli operators, they commute. They can be propagated through a Clifford circuit. And I would need real-time feedback as soon as we do non-Clifford gates like a T gate by merging with a T or an H state, like with magic states. But we're not doing that here, so it's fine. Okay, so the full gate sequence would look like this. We have the preparation, and then we have an X-type stabilizer measurement, and we do 3 rounds of syndrome extraction, ZX, ZX, ZX. Then we do the split operation, do more rounds of syndrome extraction. Now it's repetition codes, and it's only Z-type stabilizers, and then I do readout. So if I prepare the 0 state, then I will ideally get a Bell state. What I do, I prepare the 0 state, and I expect with my Pauli frame update, the way I chose it, if I would have chosen it differently, I'd get a different Bell state. But with this selection of Pauli frame update, I expect, if all the gates are perfect, to have here +1, here +1, here -1. If I just look at the final data qubit outcomes with this Pauli frame update, I get something like this. So my expectation values have the right sign, but the magnitude is not exactly where we want it to be. If I post-select all the runs and reject all the runs where the stabilizer measurement have shown that something has flipped during the cycles, if I reject all those runs and leave only the runs where no errors have occurred whatsoever, no detected errors have occurred, then I get the yellow bars. So this has the same sign. Magnitude is a bit larger, especially the ZZ observable. And this kind of makes sense because the code, the whole protocol is fault tolerant with respect to bit flip errors, whereas for the phase flip errors, only the surface code part is fault tolerant. So any phase flip errors happening after the split would not be detected. And then if I do decoding, which I'll talk about in the next slide, then I can retain all the runs except where leakage occurred, which I don't want to talk about because of time. Then I still get an improvement above the raw level. So for the ZZ observable, it's pretty good. For the XX observable, there's actually nothing to correct. So it doesn't, this protocol, there's nothing that the XX that can improve the XX errors. And for the YY error, observable, it corrects for bit flip errors. So this gets a bit better, but not for phase flip errors. So it's still pretty bad. And if we do simulations based on STIM with the stabilizer circuit simulation, with the error levels I've shown in the first slide, then we get some reasonable model of the performance. Okay, I want to talk about decoding a bit. So we're measuring these stabilizers, right? And in the first, when we initialize the 0 state, we initialize all data qubits in the 0 state. So we kind of know what the stabilizer operator is in the beginning. It's +1, because that's how we prepare the data qubits. Also in the readout, if we read out the Z observables, then we are also fault tolerant with respect to readout errors because we can construct, we know the final value of the stabilizer by multiplying the data qubit readout outcomes. Now, when we compare stabilizers from subsequent rounds, then we can see if they flipped or not. If they flipped, that indicates there was some error somewhere. So we can construct this kind of table of syndrome elements, as we call them, so parities of subsequent stabilizer measurements. So there's four Z-type stabilizers and a total of 5 stabilizer measurement cycles plus preparation plus the readout. So in the first and the final syndrome, those are comparisons of the preparation with the stabilizer measurement or the stabilizer measurement with the readout. So we have a total of 6x4 stabilizer elements. And then we also have the split operation in between where the content of the stabilizers changes. And so the definition of what is a syndrome element also needs to be Pauli frame updated. And now, one nice property of surface codes is that if an error occurs in a data qubit or an auxiliary qubit or during a gate, this at maximum triggers 2 syndrome elements to flip. So you can represent any error as an edge on a graph where the nodes are syndrome elements. Yeah, and the edges are essentially errors. So yeah, you can have this graph representation, And the edge thickness here shows how likely an error is, and these thicknesses are obtained from the stabilizer circuit simulation. The errors also can some of them flip the logical observables, some don't. So the orange one flipped the 1-bit flip code, the yellow one flips the other bit flip code, the purple one flips both, and the gray ones don't flip anything. You can also determine those weights from experimental data. So this is also called decoder priors. And so we use this method described in a paper that has been very long to get published, but it's finally there. And yeah, from these syndrome correlations from the experimental data, and this is our experimentally obtained decoding graph. Good. So, okay, I don't have a lot of time. One thing that is difficult in theory is preparing magic states. It's very easy experimentally, apparently. So what you do, you prepare the middle qubit in this distance 3 surface code in the target state that you want. And the other qubits you prepare such that these stabilizers at the boundary, they have a definite value. Okay, so you prepare these in 0, this in plus, these two in 0, these in plus, and then you prepare the middle qubit in whatever state you want. You do one round of stabilizer measurements. In this round, you don't know what the outcomes of these 4 stabilizers will be, but after one round it's kind of determined, and then you can immediately read out the qubits and see what the state fidelity of your surface code is. And we get something like 85%, and the worst states are actually Y operator eigenstates because they're susceptible to both flip and phase flip errors. What you can do is you can reject the shots where these 4 stabilizers are not consistent between the rounds. So you can't tell which error has happened, but for most of the errors, you can tell whether an error has happened. And by rejecting those runs, you can improve your fidelity quite a bit. You have to reject runs, though, but that's okay. So we can split these arbitrary states as well. We expect a superposition of plus and minus to become a superposition of plus, plus, and minus, minus. And we consider states in their YZ plane. And we see that XX, which was kind of bound to the splitting operation, that is constant. That's also what we expect. Whereas YY and ZZ, they depend on this theta angle. They oscillate, and you also get some YZ and ZY observables. So this is if we don't reject runs. Here's with rejected runs, it gets a bit better. That's not the point of it. Then we can do logical quantum process tomography. So we just take the same data. Essentially, we just take the 6 cardinal states of the surface code and do tomographic readout in the end, and we can reconstruct a Pauli transfer matrix. Okay, usually you used to square Pauli transfer matrices. This is a transformation from 1 logical qubit to 2, so it's 4 by 16. Yeah, well, you expect these 8 entries to be plus minus 1 half. They're less than that. We also see this coherent error here, which we actually trace down after the experiment. So good to know. You first need to do the experiment, analyze the data, and only then you should shut down your cryostat. And if we would have done that, we probably would have gotten rid of it, but we only figured that out when it was already too late. And the process fidelity is 0.3 for raw. That's not interesting. 0.4 for decoded. And if you post-select, it's a bit better. And you might ask, why is it so not what you want? For us, the main error sources are idling errors, meaning decoherence while the qubits are not doing anything, and errors during 2-qubit gates. So we do this marginal error variation thing using simulation. So we just plug in the numbers in the simulation, vary the numbers, and see how the error on the ZZ observable, which is supposed to be fault tolerant, varies. And we see that 2-qubit gates, there's room for improvement in 2-qubit gates and idling. but not so much for single qubit gates and readout. And the main reasons are, first of all, for idling errors, it's decoherence, dielectric loss, and the most annoying form of dielectric loss are these TLS, which is essentially just one mechanical mode in one atom somewhere. They fluctuate with time. They're unpredictable. They can be at your qubit frequency, and usually when the sample is big, you'll have at least one of them, which is like kills the whole experiment, which is kind of the problem. And then you cycle your fridge, you warm up, you cool down, it's a different one. So those are difficult to track. Then for the 2-qubit gates, there's another thing. The way we do 2-qubit gates, we vary the frequency of the qubits and we bring them into resonance. And so there's some specific pulse shapes. Thing that I want to stress here is that if you try to change the frequencies of these qubits, you need to control them with very high precision. And it turns out that the line through which you control it, that line has distortions, and the frequency is not what you wanted. And the annoying thing about these errors, they're not Markovian. We try to correct them, but there's apparently more to correct. So it looks like this is still a limiting factor, because if we just add some waiting time before and after the gate, it gets better. And this is not just for us, this is also for Google, from what I understand in the recent papers. Yes, thank you. I'm over time. That's the paper. We've got you some Pauli transfer matrices. Welcome to questions.
Thank you so much. Other questions in the back?
Yes. Okay, so there's different things. So Google can do a reset, which is very good. So they reset their ancilla qubits. It's a bit technical, so they can tune their qubits with the resonators into resonance. And this makes the readout a bit worse, and it needs to be longer. So because it needs to be longer, it's more effective to schedule it at a different time. But they get a good reset in return. So it's a choice of which circuit parameters you choose. We don't have so much idling either, but it's just the amount that we have is enough to kind of to make it bad.
Are there more questions? Yeah.
Actually, I haven't tried the STIM model so much. So if you assume equal weights, then it's like you can I wouldn't be able to tell you for this data set, but it's significantly worse if you have equal weights for all edges. The STIM model is, I suspect, pretty good, but I haven't tried it.
Jens?
Optimizing the weights from like just having the target metric, the fidelity, and then optimizing the weights. This has been looked at by Nathan, who's now at Google. I don't know what we arrived at, but we thought, okay, this is fancy, but it's cheating, so we don't do that. Yeah, you can, and it works. Yep. So we're in a grant which tells that we should be there approximately at the end of the year. Is that the answer that you expect? I mean, I'm positive we could do it. Just fix those errors, right? We know what we need to fix, right? Good. Well, let's go. Yes. Yeah. Yes, I think part of the story is that you can kind of construct your decoder. So imagine you have a huge experiment, then your decoder is going to be like a huge mess, and it's going to be like big. But you can use these parts to construct the big decoder for your experiment. So if you can characterize your parts like a split along these qubits, then you can reuse it later.
I think that was the final question. So thank you again,
Thanks.
Ilya.